Welcome to the solutions to the Regents Physics Modern Physics problem set, problems numbers 22 through 25. Number 22, a mercury atom is in excited state, has an energy of 4.95 electron volts. It absorbs a photon that raises it to the next higher energy level. They want to know the energy of the photon that was absorbed and what was the photon's frequency. A couple key terms in here to recognize. Absorbed means, well, first of all, let's back up here. The mercury atom is in an excited state and has an energy of 4.9 electron volts. So what you do is you look on the energy level diagram for mercury and you find where it's 4.95, and here we are. It's in the D state. To say that it absorbs a photon and then raises to the next higher energy level means the photon's going to come in and excite the electron even more to the E state. So it's going to go from D up to E, and that would be an absorption of a photon. They want to know the energy of the photon and then what's the photon's frequency. A is easy to do. All you do is you take 4.95 and you subtract the 3.71 because the energy of the photon has to equal exactly the difference between the energy level transition. So 4.95 minus 3.71 is 1.24 electron volts. And they want to know the photon's frequency. So you're going to use E equals HF. Notice I've chosen to use the electron volt second form of Planck's constant here. So 1.24 equals 4.14 times 10 to the negative 15, and solve for F. That means you have to divide, and you should get 3 times 10 to the 14th hertz. All right, let's move on to 23. A photon with an energy of 14 electron volts enters a hydrogen atom in the ground state and ionizes it. With what kinetic energy would the electron be ejected from the atom? Well, we're told that the electron is in the ground state, and in the ground state, 13.60 electron volts is required to ionize it. 14 hit it, so that means it will be ionized, and then the extra leftover amount will be imparted to the electron in the form of kinetic energy. So the Ke is going to be the 14 electron volts of energy that hit the electron, and subtract the 13.6 electron volts required to ionize it. That leftover amount imparted to the electron in the form of kinetic energy. So there you go. There you have it. Is a pretty easy answer also to number 23. Number 24, using the hydrogen energy level diagram in the New York State reference table. That means you should have yours out. Calculate the following energy differences for a hydrogen atom. All right, so n equals 6 to n equals 5. You take the numerical difference between those two values and subtract, and you should get 0.16 electron volts, and that would be an emission, a photon that's emitted. From 6 to 3, subtracting those two values from n equals 6 and n equals 3, 1.13 electron volts emitted. From 4 to 2, 2.55 electron volts emitted. 5 to 2, 2.86 electron volts emitted. And 5 to 3 should be 0.97 electron volts emitted. And again, all you're doing is you're taking the value of the energy it has in the initial state here and subtracting the energy it has in that final state. And you should get these respective values. Number 25. Determine the frequency of the photons emitted for each of the transitions in problem 24. Which photons are visible to the human eye? So in each of these cases, you're going to take these energies, you're going to set it equal to HF. You're going to use the electron volt second form of Planck's constant, the 4.14 times 10 to the negative 15 electron volt seconds, and solve for F. I only did C and D here, but just to take a look, I know that C and D are the only visible ones, but you should still do the answers for A, B, and E as well, and we can check those in class tomorrow if you would like to, just to be sure you're getting the right answers. But the 2.55 equals 4.14 times 10 to the negative 15. Solve for F, 6.16 times 10 to the negative 10 to the 14 hertz. You look that up on the reference table, and that falls in the green spectrum and closer to blue. That's why that's the blue-green line in the Balmer series that we've been doing in the lab. Over on D, E equals HF, 2.86 equals 4.14 times 10 to the negative 15 times F, divide both sides, solve for F, 6.91 times 10 to the 14th hertz, and you should find that to be in the blue range, but very close to violet, and that's why we call that the blue-violet line. All right, that'll do it on our solutions for numbers 22 through 25. We'll wrap up this problem set tomorrow in class when we do problems 26 and 27 together tomorrow.